So here's another fun word to say, stoichiometry. It's fun to say, but it's a really powerful technique in chemistry. So we're going to learn how to do that today. To start with, stoichiometry is a process, a problem-solving process, by which we can predict amounts of substances involved in a chemical reaction. It comes from two Greek words, the Greek word stoichion, which means element, and metron, which means measure. So literally, stoichiometry means to measure elements. But it's so much more than that. I like to think of it as a way of predicting the future, because I can take a look at a chemical reaction and some information about my starting materials, and without even going into the lab, I can predict what's going to happen, down to how much product I should be able to make. Pretty powerful. It's also arguably the single most common calculation done in any chemistry lab anywhere in the world. Stoichiometry calculations are used all the time in all laboratories because it's a way of not only predicting what's going to happen, but evaluating whether or not your experiment's any good. And we're going to learn how to do all of that. The central part of stoichiometry, it all hinges on something called the mole ratio. Okay, so the mole ratio is the ratio of moles of one substance in a reaction to moles of another substance in a reaction. And basically, it's given by the balanced equation. So if you have a balanced equation, you can determine any mole ratio of any two substances because you're going to use the coefficients, the big numbers in front, to represent the number of moles of each substance. So for example, CH4 plus 2O2 goes to CO2 and 2H2O. That's a combustion reaction, burning of methane gas. I can find any mole ratio between any two substances just by looking at the coefficients. So for example, this reaction tells me that for every 1 mole of CH4 that I combust, I'm going to produce 1 mole of CO2. I'm also going to produce 2 moles of water. If I want to combust a mole of methane, I have to have 2 moles of oxygen in order to completely react it. So the mole ratio is very simple, but very powerful, and it's the central part of this stoichiometric technique that we're going to learn. Okay, so let's just get some practice with that. So we have aluminum metal reacting with a solution of copper 2 nitrate. We want to know the mole ratio of aluminum to copper 2 nitrate in this reaction. All stoichiometric problems begin with a balanced equation. Okay, so here's an unbalanced equation. This is aluminum, copper 2 nitrate, combining or reacting, single displacement reaction, to form copper, metal, and solid aluminum nitrate. Nothing new here. We've done plenty of this before. I need to balance this, so let me put in my coefficients. So 2, 3, 3, and 2, the way I have it written here. So what's the mole ratio of aluminum to copper 2 nitrate? Well, both aluminum and copper 2 nitrate are my reactants, so I look at the coefficients in front of them, and I see that there are 2 moles of aluminum for every 3 moles of NO3,2. So the mole ratio is 2 moles of aluminum over 3 moles of CuNO3,2. Pretty simple. Okay, so that's how we find mole ratios, and we're going to use the mole ratio as part of our calculation. We use it as a way of converting information about one substance into information about a different substance in the chemical reaction. And oftentimes that's what we're going to be looking at. Maybe we know something about the reactants, and we want to predict something about the products. Well, we have to convert one substance into another. We have to get from information about one substance and start talking about information about another substance, the products in this case. Okay, here's another example. So we want to know how many moles of hydrogen gas would be needed to react with 4.55 moles of nitrogen in the following reaction. Now again, you always need a balanced equation to start. So here's the reaction for the production of ammonia. Nitrogen gas, N2, plus 3H2 goes to 2NH3. So our mole ratio is 1 to 3 to 2. For every 1 mole of nitrogen, you need 3 moles of hydrogen, and you will produce 2 moles of ammonia. But in this case, I'm interested in, I don't have an exact round number of moles of nitrogen. I have 4.55 moles of nitrogen. So I'm going to set this problem up. 4.55 moles of nitrogen, that's my given, that's what I'm starting with. And then I use the mole ratio. Now I have moles of N2 on top, so I'm going to cancel moles of N2 by putting it on the bottom, because I don't care about moles of nitrogen. I know how many moles of nitrogen I have. What I care about is how many moles of hydrogen. So I need to cancel moles of nitrogen. And I need to leave myself with moles of hydrogen, so that one has to go on top. The general rule is it's moles of what you've got on the bottom and moles of what you're looking for on the top. Okay? So it's a 3 to 1 mole ratio, 3 moles of hydrogen for every 1 mole of nitrogen. I just have to multiply 4.55 times 3 and then divide by 1, which is just multiplying by 3. I keep the same number of significant figures as my given, the number I started with, which was 4.55 moles, so my answer is 13.7 moles of H2. That means if I want to react all of that nitrogen away, I have to have 13.7 moles of H2. So using mole ratio is useful. You know, it's easy. Moles are the central unit in chemistry, but we don't have anything that measures moles in the lab. We can measure grams of stuff, right? We can measure molarity. We can measure volume of gases at STP. So we're going to use those tools that we already have to do more complex, more useful problems. Okay, here's an example. What mass of magnesium oxide would be produced when 0.150 grams of magnesium metal reacts with an excess of oxygen gas? I'm about to predict the future. I'm not even going to do this experiment, but I'm going to predict how much product I should be able to make, given that I'm starting with 0.150 grams of magnesium and as much oxygen as I need. So the first thing I have to do when solving a problem like this is start with a balanced equation. I always start with a balanced equation. So a magnesium metal reacting with oxygen gas to produce magnesium oxide, balancing it 2 Mg plus O2 goes to 2 MgO. Synthesis reaction, right? All right, so given that information, that's where I'm going to get my mole ratio from. And given the fact that I'm starting with 0.150 grams of magnesium, let's set up the calculation here, okay? I start with 0.150 grams of magnesium. Now, I can't work a mole ratio unless I have moles. So the first thing I'm always going to do in stoichiometry is get to moles if I'm not already there, because the mole ratio allows me to go from moles of one thing to moles of another. But that means I have to start with moles of something, right? So the first thing I'm going to do is I'm going to use the molar mass, 1 mole of magnesium over 24.31 grams of magnesium. That's the molar mass of magnesium, and that will convert grams of magnesium to moles. Now, according to my balanced equation, there are 2 moles of magnesium oxide produced for every 2 moles of magnesium metal consumed or used. Moles of what I'm trying to figure out goes on top. Moles of what I've got already goes on the bottom, so it's 2 over 2. Yeah, you could write that 1 over 1. I never will, because I want you to know where those 2's came from. But it's not wrong. If you realize that 2 over 2 is the same as 1 over 1, go ahead and do it. I always write it. The numbers that appear in my balanced equation are the numbers that I'll always write in my mole ratio. Okay, and then I can do the canceling later on. And finally, I was interested in what mass of magnesium oxide was going to be produced. So I need to use the molar mass of magnesium oxide, because once I get through the mole ratio, I'll have moles of MgO, but I wanted mass of MgO. And so to go from moles to mass, I need the molar mass of MgO, which is 40.31 grams. So it's really 2 mole calculations, 2 one-step mole calculations with the mole ratio in between, joining them together. That's really all this is. Okay, so I multiply across the tops, 0.150 times 1 times 2 times 40.31, multiply across the bottom, 24.31 times 2, and then divide. Keep the same number of significant figures as the given, the 0.150 grams, so I get 0.249 grams of MgO. Okay? It looks more complex than it actually is. All I'm doing is continually canceling units I don't want and leaving myself with more desired units. All right, you try. Your turn. You're going to stop the video after you write down this problem and see if you can do this calculation. Okay? Here's the problem. I want to know what volume of carbon dioxide gas at STP. Now that should set off ringers in your head. I should know that means something. What, right? Volume, STP. That means a specific relationship that I know. Would be produced if 2.750 grams, there's another keyword, grams, I know what that means, of ethane gas, C2H6, was combusted. Okay? Stop the video. Don't forget, start with a balanced equation. Okay? Write the equation out first, and then see if you can follow the example that we've already done to figure out what volume of CO2 you'll produce when you start with 2.750 grams. Stop the video and give it a try, and then come back and we'll see how you did. Are you ready? Okay, so first your balanced equation. 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. That, if your balanced equation isn't right, you can't possibly get the right answer. So that's why we did that first. We learned how to write equations and balance them first. So there's my equation, and I have my mole ratios available. Okay. Now let's set up the problem. We know that we're starting with 2.750 grams of C2H6. The first step of any stoichiometric calculation after I've got my balanced equation is get to moles. So I need the molar mass of C2H6, which is 30.08. So 1 mole over 30.08 grams. That'll cancel grams out and leave me with moles of C2H6. But I'm not interested in moles of C2H6. I'm interested in CO2. So I need to use the mole ratio here to get to CO2. Well, according to my balanced equation, there are 4 moles of CO2 over 2 moles of C2H6. For every 2 moles of C2H6 produced, I'll produce 4 moles of CO2. Yes, you can write 2 to 1. I'm not going to do it because I want you to see where those numbers came from. The 4 was in front of the CO2 and the 2 was in front of the C2H6. Again, remember, moles of what you're trying to figure out on top, moles of what you've already got on the bottom. And then finally, volume means that once I have the moles of CO2, which I will have after this third step here, I want volume, liters. Liters is 22.4 liters per mole. And so I have to put moles of CO2 on the bottom of my last conversion because I want to cancel that and leave myself with liters of CO2, which has to go on the top. Okay, so we've got like 2 problems here. One is a mass to moles problem, the other one is moles to liters, and they're joined together by this mole ratio in the middle. So the answer that I should get is 4.096 liters of CO2. The 4.096 has 4 sig figs because my 2.750 grams at the beginning had 4 sig figs, and that's the one I look at. So that's how you do stoichiometric calculations. Do they get more complex? Maybe a little, but the general idea is always the same. Start with something, get it to moles, use the mole ratio to get to moles of something else, and then do something with that to get your final answer. Always start with a balanced equation. Can't stress that enough. Give it a look. Look over the video if you need to. Again, we're going to get plenty of practice with this.